a function, and we can express that in terms of this order of coordinate, and then by just taking the composition. So that's and an example would be, for example, we can look at the map which is x, y, and z equal to z on the sphere. So on the sphere that we had. And then what we need to do is like, we can, for example, take again the same map that we looked at before, where this one was mapped to x, y, that was our chart. So what we have to do is like we have to pre-compose that with f. So what we have to look at is like this composition, where we first go to the map phi, and then plug that in f. So this one is nothing else than plugging in phi first in f. So we do that. So it's f of x, y, 1 minus x squared equals, and then now this function f is defined by this c component, so this just gives us and this one turns out to be smooth. You can check that by taking the derivatives and stuff. And now you have to check that like for all of the different order charts that I described before, where you cut out like a different part, and then you end up with like also like a slightly different function, and you have to check that it's also smooth. Checking. And there's a nice result, which I don't want to go like too much into detail, is that, for example, on the sphere, we saw that there are different kind of coordinate systems, right? Like that you have like the coordinate systems of like polar coordinates and the systems that like these kind of coordinates here. And the nice part about like this concept of smoothness is that it doesn't depend on which chart I can choose, as long as the charts in itself are like compatible. But I will not talk about this compatibility like too much. But it's like something like for the people that are a bit more mathematically oriented, they might be like, the natural question is like, okay, now this depends on all compositions, so that's usually very hard to check. Do I have to really check it for all, or like is there like dependent on which kind of charts I choose or not? So that's like answered by this statement. It's if the charts in itself are compatible, namely that like certain kind of maps are smooth, then it doesn't matter which chart you choose. So it's, but I don't want to get like too much into detail for this course. So that defines you the concept, like this one, defines you the concept of a function that is smooth on the surface. But it's usually more like simple to talk about or like to study a surface by looking at like things that like map into the surface. So for example, we could like look at like curves in the surface, which usually describe a little bit more like the geometry of the surface than a function that is defined on the surface. Like in mathematics, there's like essentially two ways to study objects. It's like either we define objects that live on the thing that we want to study, so like smooth functions that live on the surface, and we like derive certain properties from that, or we look at like things that map into the surface. So these are like the two different ways to study things. So in this context, is this important that like some curve which is living in R3, and we see that this one is a smooth curve in the surface. If C of t is always an element of the surface. So we have like a nice parameterized curve, which is like nice, and we describe that in like 3 coordinates. And we say that this one is a smooth curve in the surface if it just takes values there. And equivalent, but it's a bit like harder to show, is that we can check it also with the charts, namely that the composition with the inverses, which are maps from I to R2. So yeah, like you can also check that with the charts, but not get too much into that. But like a nice property that we get like certain curves automatically once we have a parameterization of some subset. And the way is that, like, if you think about a surface as something that is like taking this sheet of paper and curl it, then you automatically see there are certain curves on that surface. Namely, like we have the red ones and the black ones, like the things that goes in x direction and the things that go in y direction. And that one are mapped to smooth curves on the surface, right? Like we have now the red curve, but this one goes around on the surface. So it stays on the surface, and that's naturally defined by just like choosing this parameterization. So the following example. That's that guy's parameterization. Then the curves, here C of t, which is defined by this t equals to 0, which we can always arrange that to be a part of t by saying like 0, 0 has to be in d, and then just like making t small enough. You can take the composition, also phi of c of t, which is nothing else than a smooth curve in R3. But of course, almost by construction, that point here is always an element of S, because it's like a parameterization. So that the images of phi, like S is defined as like locally at least like the images of phi. So because this one is direction S, you can see that this map which maps to these ones define like a certain smooth curve. So once you fix the origin at, like say, like the origin is here, then this one would be like the red line. It's like this curve C of t. It's like just like going in the x direction. Actually, it goes up. Yeah. Yeah. Like y is this 0, so like it goes in this direction. So like that's the curve C of t is the red line. And now if I like curve it, and it's like this this curve which I wrote down here. It's this curve is like now the red line, but just like as a curve on this curved object. So that's like a particular class of lines. And now we would like to talk about directions. And the way we talk about directions is by saying we take derivatives of functions, of curves. So we saw like a tangent vector, we would define that as like as a derivative of a certain function, of a certain curve on the surface. Which is usually denoted by n, by x, at some point in S. Is a vector it's a vector in R3, but we would like to say that this vector is like tangent to the surface, right? Like so, if the surface looks like this, then of course I can say like this one is a vector at that point, right? Like, but it's not like tangent to the surface. So what we would like to say is like it has to be a kind of going in the surface, but like or along the surface, not like just something like normal, like it just like should not pointing down. So we would like to have something that is going like in the direction of the surface itself. And that the way we talk about that is like in terms of the curves. We have a smooth curve in S such that it starts at that point M, and it has like we take a time derivative such as a vector to get it. And because we require that's important, it's like a smooth curve that is lying inside of S, requires that like you can't get out of the surface with the curve. So that also means like ensures that like you can really think of the tangent vector as something that is like tangent to the surface. So that's why it's called tangent to the surface. And set for tangent vectors at some given point. For the tangent space. denoted by Tm. So it's really like the S says for the surface, the M says like at which point I choose like as my reference point, and the T is then say like please take all of the tangent vectors at that point. So that's for tangent plane or tangent. Particular, if you look at that example that I wrote down here, if you take the derivative at 0, so if you take e of t at 0 of this curve, this is nothing else than taking the derivative of phi in x direction at the point 0. So that means this vector, which is like a vector, is a tangent vector at the point where the chart is centered. So again, not using, maybe I'm overstretching it here, but again, this example, we have this curve, which was the red curve, which goes in x direction. So we can think of that now as like some small vector which is attached to say like this point, and then now we curve that, the whole thing, something like that. So the red curve like goes around here, but like the vector that we can represent this is like just like the first derivative. So that would be a something that is like my finger like this. So it goes like along the surface, and it's the first like approximation of the curve. So and of course we can do something similar also with the y derivative. So maybe it's like instructive to look at like the following case, namely we let this one just to be open, and we can think of that as a parameterized surface with this parameterization being just the identity. So we don't change anything. So that we can like just like an open subset, we can always think as a parameterized surface. And there would be like these vector fields which are going in this one direction. So for every point which is sitting in D, we can consider start in x0 and y, and then going in the x direction. So this one. Interval has to be small enough so that I don't get out of the at some point. This one is starting at the t equals to 0. We just get our point back. And moving back from x with the time derivative at the curve equals to 0. So we just take the time derivative and then we get the points. So the picture essentially is we have our t, and then at each point you have like a small little arrow attached that goes in the x direction. And of course, you can also do that with like the y direction. Okay. So from this example that I showed you before, is that if you have a parameterization, then you have like these like the vectors where you take the partial derivative in x and the y direction. These are tangent vectors at the surface. That was like what we discovered. And there's like, actually it's a little bit more. It's true. Maybe they are like very natural things. So if you have a parameterization of your surface, or like a chart, essentially, maybe write it. Coordinate chart of the surface centered at the point so 0 is mapped to some point in the surface. Then every tangent vector x is a linear combination of these two vectors. And linear combination means that is for every x you can write it as v1 times this vector. So we call this one is really like a vector in R3. we find some constants so that any vector, regardless of what we can choose, is of this form as like something that goes a little bit in this x direction and something that goes a little bit in this y direction. Okay, so let's have a look at the proof. So first of all, we already saw that these elements are really elements of the tangent space. That was this argument here. So there's nothing to check. But what we have to check is that once we have an arbitrary vector, we have to find like these v1 and v2 so that we can express it. So because it's a tangent vector, we know that there exists smooth curve in S such that it starts at a point and the first time derivative at 0 is exactly the vector that we started. Because that's the definition of a tangent vector. What we do now is define a curve which is a curve in R2 by using this chart that we have. So we take the inverse. So we maybe have to shrink this interval a bit. Maybe we need to shrink that a little bit. Because otherwise we might run out of, like the curve might leave the definition of where this inverse is defined. But for small enough times that we can define. And then almost by definition we have the following, namely that we apply phi to let's see phi of t, then what you get is c of t. So that's just like a different way to express the definition. And now we take the derivative. And we can use the chain rule to take the derivative of the left-hand side. So what we get is that we take the derivative of phi first, and then we have to evaluate that as at the tangent vector at 0. But this one is, you can take the right-hand side to take the derivative, which would be the tangent vector at 0, and that one was by assumption our vector x. So this one is some vector that we don't know. So this one at 0 is some vector. It's like a vector in R2, which we don't know, but like it has some components. See like this. And there's a nice result that we had last time, namely that P0 phi is a linear map. That we had like last time. And we also had last time that if you evaluate this one at the x direction, and this is nothing else than taking the partial derivative at 0. So that was just like the definitions from last time. It was two properties. So we now use these properties here. So what happens is that you have which is C phi of 0, which is like V1 and V2. And now we use linearity, which means that we can plug out V1 these vectors. And now we use the second property that we know what this one is, namely but this is exactly what we wanted to prove, because from this equation upstairs, we know that the left-hand side is x. So x equals to this guy, where this guy we just like calculated this expression, which we can write as a linear combination of this. And that's exactly the statement that every vector can be written in this way for some coordinates. So you show, like what this argument shows is that these coordinates are given by this kind of like construction where you take like a certain curve in R2 and then they take the derivative at 0 of that curve. Okay. So the point of like why do I go like through the proof of this lemma and what you have stated is that it gives you an important information about the tangent space. It says namely that every element of the tangent space is like of this form where we have like these two vectors and then just some constants. So that means that we can declare these two vectors that we get here to be a basis, and they are never parallel. It was like the regularity assumption on the chart that we had. So since dx and dy are not parallel, that shows us that the tangent space is a two-dimensional vector space spanned by these two. We have a two-dimensional vector space and like a basis given by these two vectors. Maybe in the last few minutes, let me have a look. Show you an example. And the example is that we take again our sphere, and so if you have like smooth curve in the sphere, then what we know from that, if you take the norm squared of its of the curve, then it has to be equals to the radius of the sphere, so it has to be 1. So what we can do is we take the derivative of that expression in t. And what we get is that we have c of 0 times 2 times first derivative at 0 equals to 0. But this one was just say like it's the point on the sphere, and this one is the vector at the sphere. So that maybe it's quite a point as p. So that follows that the tangent space at some point on the sphere are all the vectors in R of 3 for which the inner product of p times x equals to 0. And the picture is this: we have our sphere. We take the origin, and then we get like a vector, which gives you the point. So that's p. And then from this picture, you see that the tangent space are all the vectors which are like orthogonal to p. So the tangent space that we calculated here are all the vectors that are like orthogonal. And again, like one way you see that it's really all of them is like using this argument because there is clearly one constraint, one linear constraint on x. So the degrees of freedom of this space are like 2-dimensional. So by this argument up there, that it's like has to be 2-dimensional, then we know that all of them are really of this space. So that's like one way to prove that. It's usually by constructing some property and then saying that this property has to be fulfilled by all curves or vectors. Okay, and I think that's all I wanted to talk about for today. I still have one thing that I would like to do with you. Namely, I would like to get like a bit of feedback, what you like and what you don't like about the class. So just take out like a very small sheet of paper and just like write down something positive that you like about the course and something that you don't like maybe, or that where you say like that I would like to see improved. Just like some very short thing. Don't put your name on there, whatever you want. Like it's completely anonymous. I just want to get like some feedback for myself so that I can improve myself and I give a better lecture to you. So just write down something that you like about the lecture and the way I give the lecture, and something that you would like me to change. Yeah. So if you don't have a sheet of paper, just ask around. Someone else probably finds it. Yes.
I'm a graduate student.
Yes.
I have sent an email to you.
Yes.
Yeah, and this is the first time that I joined the classroom. So I'm wondering which one is teacher assistant, teaching assistant, and
Yes.
I'm going to join your WeChat group.
So here it's Tong Wang, I think it's called.
I don't know her which
so,
name. You can show me the okay, thank you. As I said, I can only finish the homework late.
Yes, so I informed the TA and he is fine with it.
Yeah. Okay. About the recent days after I will have some questions to ask her.
Yes, makes sense.
Yeah. Okay. Thank you.
Yes. Yes.
I'm confused with the denotes of the T005.
Yes. Wait a second. So just bring out like the sheet of paper to the front and like just put them on my desk. I don't look at them now, just like when I'm home. So just put them there. I don't. So, yeah. So this. So if you have like T00 bias, this one is the surface, and this one is like all tangent vectors. If you have like 0, 5, that is just a map. This is actually a map. This one is a map. So like this one is just 5. Then this notation of like T00 is actually just describing the linear map that we had like last time. So like this one is a map from R2. This one is again this one is like we defined that from last time. This one writes the last vector. So this one is like this vector. So it's really important, like here we have the surface, and here we have a map. Yes, you can. So you have like this one. This was okay last time. We have a map from R to R3, and this one is a linearization. Which you can think of that essentially as this matrix area. That's what's the main question. Like it's a big like one vector here and another one here. That's Jacobian. And that one defines the map from vector to vector. So that's like the last one what we have. You have a map, then you get like a linearization. So it's giving you the linear. But now it's like really about the circles and taking over. And next time I will explain like why that notation is kind of nice. Ah, okay.
现在看一个切空间，就是某一点的所有的函数，在这一点导向相同的函数，假设那个还是压的机。搞不懂，好像学的稀里糊涂，感觉我一辈子前19年、前20年没有接触过几个。我以为他那种他们这样是大概说，结果我下了一种，结果打进出来发现不是自己看了。
Very confusing. What you have is like gamma. You have gamma. You have a curve. And then you have a circle whose center lies inside gamma. You have a circle inside gamma. And then you need to invert it. You don't know what that means.
就讲这个结束了，连那个高里面那个玩意儿，
that is applied to an inversion with respect to the circle. But I think it's you have like this circle, and what you do is like have this circle in there. What you do is now take this one here, connect that to the origin, and then you invert it. Just part like something here. So what we end up with is like a curve inside. This one is I think it's for gamma. Yeah, so it's like if you have if you think this gamma is something of form half in some direction. That's the radio. Around this like theta gets circular like radio 1. And gamma 1 would be a 1 over r here, but the same direction. I think that's what you want, but I'm not totally sure. It's like very strangely written, but that's what I would like guess, is that you have like something where you say like to measure if this one is the radius r of t. Yes, and then you say like this point here, this curve here, radius 1 over r. So that's what I suspect is meant, but I'm not totally sure. Makes sense.
Let me think at night.
Okay, good. Yeah, but I agree. That's like very, very strange.
About the coordinate chart, so this thing is so why do we need this open subset from the three-dimensional? Why can't we just say, for example, I just don't understand, like, so the process here, are we proving, like, what are we trying to prove? Are we, or we're just showing that?
So what we show here is that like this construction is like really a chart. Like the definition of the chart is just that, like it has these three ingredients.
Yep.
And then here what we do is like, okay, we write down the three ingredients and then check at least some of the properties that they have to satisfy. That's what's done.
Also, we're trying to check this.
Yeah, so we checked, like, for example, that this condition on the image of the parameterization, that this one is equal to the intersection of that.
So why do we intersect the S with the open subset from the R3? Is it because that we are trying to create like a open subset within the S?
Yes, so there's like different ways to view that. Like, yes, so like what is, like you can, in some way you can just remove that. But what then happens is that like you get maybe very strange things where this, what, like you probably know that from, do you know topology a bit?
I don't, unfortunately.
Okay. So what is like, if you have like a collection of open sets, that gives you something that tells you how close by points are.
Okay.
If they're like in an open subset, then they say like they are relatively close.
Oh yeah.
So that's like the measures like the distance between them. Okay. And if you have like some subset, what you then do is like you just take the intersection of all open sets with like the subset to get like another set which is contained in that. So like these parts here, this S intersected with O is kind of like a measure of like closeness relatively to the topology that you can, like that you know, like when 2 points are relatively close by in R3, you don't have like that. What could happen here is that like your map takes 2 points which are close by, but like brings them very far away in R3. And you don't want that, because then if like you want in some way, like what this says is like the point